Well, we've made it to the end of Unit 6. This is our last lesson, 6.8, where we're going to look at integration of transcendental functions in particular. I'm just restating the rules for all the trig functions here and the log and exponential functions here, and then the inverse trig functions that are most common here. There's also times when we might want to use identities, double angles, and some of the Pythagorean triples, power reducing. So let's look at this first example. We want to use a u-substitution right away. If u is natural log of x, then our du is 1 over x with respect to x, because you can see this mentally if you think about 1 over x here and 1 over natural log of x cubed here. When you put those together, this is my derivative part that's hiding within that integrand. So we're going to rewrite that as 1 over x times 1 over 3 natural log of x. I'm just using the properties of natural log. With respect to x. And then my 1 over x dx is going to be the du. We can pull the 1/3 out as a factor in front of the natural log of x. If natural log of x is our u, then we have du over u, and that becomes 1/3 natural log of the absolute value of u plus the constant. But our u was a natural log, which makes our indefinite integral 1/3 natural log absolute value natural log of x plus a constant. In this case, we're looking for the piece that's going to be the derivative if our denominator is the u-substitute. And we have a derivative for that denominator in the numerator. It's just off by a factor of 3. And we saw earlier in the last lesson that you could divide through by that 3 to reconcile the difference. And then integrate 1/3 of du over u, which is 1/3 natural log of u, but our u is 2 minus 3 cosine theta. And then remember to add plus c. On part C, you notice most of the time our denominator is our u-substitute. So derivative of sine is cosine. And again, this is du on the top and u on the bottom for natural log of u plus a constant, and go back and back substitute 1 plus sine t plus c. Here's one using an exponential, so I guess, let's see, e, this is really messy. So let's do that. We've got a half x cubed as our exponent on the e function. That derivative is 3 over 2 x squared. We need to get rid of the 3 over 2, so divide by 3 over 2. And then we can set up the integral. So 2/3 of the integral of e to the u du is just e to the u, but u was our x cubed over 2 plus a constant. Well, that's pretty straightforward. Let's try this one. So maybe cotangent, because derivative of cotangent is negative cosecant squared, and I'm thinking about sine on the denominator is cosecant in the numerator. Follow along with that? If u is cotangent, du is negative cosecant squared, which is the same as 1 over sine squared on the bottom. So we're off by a negative. And there's a dx in the numerator and a sine squared in the denominator, which balances out perfectly as long as we pull the negative out front. So we're integrating e to the u du, which is e to the u plus a constant times -1. And u turned out to be cotangent. So piece of cake, that was pretty simple. Moving on to the example F, our sine is a power, and the derivative of sine is cosine. That little piece is in our problem. We're going to integrate 2 to the u du. And that rule, anytime I have a base a to the u power, the antiderivative is a to the u ln a on the denominator and u prime. Let's see. So our a value is 2, or a is 2, and u is sine. So we can back substitute here and here to follow that integration rule. 2 to the sine x divided by natural log 2 plus a constant. So just a matter of memorizing those formulas so that they'll be fresh in your head when you need them. Okay, this one looks like an inverse tangent to me. And I'm seeing a is the square root of 5, because this is a squared plus u squared. And our u would be 2x, since 2x quantity squared is the 4x squared. And maybe we'll just make a note in our head. This is tan inverse of something. So we believe that's tan inverse of something. So there's no 2 in the original integrand. So we would want to be, if u is 2x, then du is 2 dx. Du is 2 dx. So we divide by the 2, bring that half out to the front, and rewrite it so that it looks like tan inverse. And you can see the square root of 5 quantity squared plus 2x quantity squared with the dx on the top. We don't have variable agreement. Let's clean that up. Thinking of it that way. Whoop. So the rule is 1 over a, and our a is square root of 5. So 1 over a tan inverse of u, excuse me, over a plus a constant. So 1 over 2 radical 5 would look a lot prettier. We put this together. 1 over 2 radical 5. Tan inverse of 2x plus c. All right, not so bad. Group that up and make it a little bit smaller so we have room for the next one. All right. So here, what would be a good u-substitution? Let's say sine inverse, because sine inverse is 1 over the square root, so this is our derivative down here. U is sine inverse, and du is 1 over square root of 1 minus x squared, which is definitely our denominator. That just leaves us integrating u, which gives 1/2 u squared plus a constant. And our u is sine inverse of x squared plus a constant. Okay. Let's try example 2. What's this about? Find the definite integral. So those were indefinite integrals. Now we're back to changing the upper bounds and the lower bounds. In this case, our u could be the denominator, x plus cosine x. And du is 1 minus sine x. There's our numerator. But when x is 0, u would be 1 plus cosine 0. So u would be 1. Wait a minute. Okay, had to get a drink. Let's see. So if x is 0, then u is 0 plus cosine 0. That's 1. If x is pi over 2, then u is pi over 2 plus cosine of pi over 2. So that would be pi over 2 plus 0. U is pi over 2. And we're rewriting our integrand in terms of u. We want to start at 1, stop at pi over 2. Pi over 2 is about 1.5, a little bit larger, 1.57, so it's larger than 1. And we're integrating du on the top. That's our du. U on the bottom. We're looking at natural log of u, evaluated from pi over 2 to 1. And both of those numbers are positive, so we don't have a problem with that. Having to be absolute value. Natural log of 1 goes to 0. And then our final answer, or definite integral, is natural log of pi over 2. No plus c needed. Definite integral. And then on B, we'll use the power of 2 minus x. The derivative of 2 minus x is negative 1 dx. When x is 1, u is e to the 1. 2 minus 1. When x is 3, u is e to the 2 minus 3, or e to the negative 1. Wait, I'm going here. I'm saying the wrong thing. When x is 1, 2 minus 1 is 1. When x is 3, 2 minus 3 is negative 1. I was looking back here thinking about that. Don't let me confuse you. Okay, leaving all the x's behind and integrating, we need a negative in front. We need 1 on the bottom, lower bound, upper bound. that's already wrong. So we're going to have to flip all of this around in a second. We want the lower bound to be smaller. So using that property, it's the opposite. That turns this positive, e to the u. The antiderivative of e to the u is just e to the u, evaluated from 1 to -1, or -1 to 1, I should say, which gives us e to the 1 minus e to the -1. And e to the 1 is 1, and e to the -1 is 1 over e. This is the exact answer. Oftentimes we'll need to find an approximation on AP question, so it could also be a decimal approximation, just in case you need that. And a couple more on this example, and then we'll have a few completing the squares and changing variable challenges. Okay, e to the 3 over x and x squared in the bottom. Let's use the power on this. So if u is 3x to the -1, du is -3x to the -2, which looks like a -1/3 comes over here, and the 1 over x squared dx is built into our problem right there, since it's in the denominator. And we want to change the variables. Do we need to do that? Let's see. When x is 1, u is 3. When x is 3, u is 3 over 3, u is 1. How interesting is that? So in this case, when we changed the bounds, the lower bound became the upper bound, and the upper bound became the lower bound. So if we were to integrate like that, our new lower bound would be 3, and this would be 1, but we have a -1/3 in the front, e to the u du. When we flip these around to make them in the proper order, 1 to 3, that turns this negative into a positive. And it's a piece of cake, all downhill from here. E to the u, evaluated from 1 to 3, times 1/3. So 1/3. Here, let's see if we can just write the answer in a prettier format. We've got e cubed here, and e to the 1 here, divided by 3. Or if you wanted to factor, you could factor out an e and say that's e times e squared minus 1 over 3. And that's roughly, on my calculator, 5.789. So if I was working an FRQ, I'd stop here, right at the first one. But you could have any of those three on a multiple choice and be able to track that down. Okay, last one in this example, I believe. Nope, 2 more to go. So let's see, let's try the denominator for the u substitute. And that derivative is 2e to the 2x dx, which is our numerator up here. Replacing the bounds, so changing the variables. When x is 0, u is 1 plus 1, so u is 2. When x is 3, u is 1 plus e to the 6th. That looks like it would be something with calculator related. So 2 for our lower bound and 1 plus e to the 6 on our upper bound. We're integrating du over u, which is natural log of u from 2 to 1 plus e to the 6. And natural log of 1 plus e to the 6 would be a positive number anyway, minus the natural log of 2. That's my exact answer. And if I wanted a decimal approximation, about 5.309. So either or. And then e, we'll have u as x squared and du is 2x. So we're off by a 2. We have an x. When x is 0, u is 0. When x is 1, u is 1. That happens sometimes when the bounds don't change. So 0 to 1. We need a factor of a half in front. 5 to the u is our rule. And that follows that we have 5 to the u over ln of 5 evaluated from 0 to 1, which is 1/2 5 to the 1 over natural log of 5 minus 5 to the 0, which is 1 over natural log of 5. We can combine those. Oh, got a mistake here. Put a 5 down there. Need a 2 down there. So what does that look like? 5 minus 1 is 4. 4 over 2 natural log of 5. And if you care about reducing, we could reduce that down to 2 over natural log of 5, which is not necessary on the AP exam, you know. And if I needed a decimal value, I've got about that. This is exact and approximate. Okay, so last one on this set. We'll call u the power on the cosine of x, and the derivative is negative sine x. So we're off by a factor of -1. And when x is 0, u is 1. When x is pi, u is -1. And integrating. So we need a negative for the derivative. We're going from 1 to -1, and already that's backwards. E to the u du. We'll flip that over and put -1 down here, +1 here, and make this a positive e to the u. And then evaluating that antiderivative from -1 to 1 gives us e minus e to the -1. And didn't we just see that answer on another question? Oh yeah, on letter B. Similar. Same answer, different question. And then here, evaluate by completing the square. So we saw this earlier. Remember, this is one of the things that College Board is going to add for us. So I'm thinking that if we rewrite this as 36 and 1, we could call that a complete square by just visualizing that. And we would have dx on the top and rewrite that denominator as x plus 6 squared plus 1. You see tangent inverse in this, 1 over u squared plus a squared. So 1 over a is 1 over 1. And tan inverse of u over a, that's x plus 6 over 1 plus our constant. So those are things you just have to get used to, recognizing those patterns. And the more you work them, the more you start to see them. So I'm looking at taking, in this example B, taking the negative out front and thinking about completing the square so that we could create a sine inverse. This, we want to turn this into a sine inverse somehow, right? How can we do that? So half of 4 is 2. 2 squared is 4, but we would need to balance that out with adding the 4, because in this case I'm subtracting a 4. So I want to add a 4 to keep that equality there. Okay? So thinking about the denominator that way, we're integrating dx over, let's see, 4 minus x minus 2 squared, right? I got to put the square root here. Okay, following what I've got this 4 minus this term, this trinomial is the x minus 2 quantity squared. It's all under the radical. That's how I recognize that this is a sine inverse integrand. Sine inverse, and we have the u x minus 2 over the a, which is 2, for the argument, sine inverse. There's that little rule that's on the first page of our lesson, just so we can go back and revisit that. Nope, second page, right here. I was seeing that in my head. We had a 4 here, so a is 2, and we had an x minus 2 here to give us, where did it go? Oh, that's a lot of pages to give us that. So the u over the a. Those are tricky. Then a couple of challenging ones. Let's say, I think I might put that on a separate page, so we can duplicate this page. Okay, so get rid of that one, and let's think about this one. Says it's a challenge. So if our denominator is the 1 plus the square root of 2x, and we need to solve for square root of 2x, let's take the derivative. So the derivative of this side is du, and the derivative of this is going to be, let's see, 2x to the half. So we're adding 1 to that. Oh, derivative, we're subtracting 1. 1/2 times 2x to the negative 1/2. Ooh, that's a common problem. You see, my brain just went to integrating, and I was really deriving. So 2 on the bottom, 1 over 2 times 2. Ooh, just lost it here. So we got 1/2 times 2x to the negative 1/2 chain rule times the derivative of the inside. So our derivative du, this cancels off this, And we have a 1 over square root of 2x. Mercy. So square root of 2x, what are we going to do here? Look at this. This is a challenge. You see how the square root of 2x could be called u minus 1? And I've got a square root here, 2x. So let's say we cross multiply and put the square root of 2x with the du. That's equal to dx. Replace this with u minus 1. So u minus 1 du is another name for dx. Whoa, this is definitely a challenge. And we're going to integrate what's in the top, u minus 1. So dx is u minus 1 du. So I'm replacing this. Dx is u minus 1 du. And in the bottom, 1 plus radical 2x is my u. So how about if we break this fraction apart? U over u is 1, and 1 over u is 1 over u, and integrate that way. So the integral of 1 is u. I'm going to come down here a little bit more. The integral of 1 is u, and the integral of 1 over u is natural log of u plus a constant. But what was u? U is 1 plus radical 2x. So 1 plus radical 2x minus the natural log of 1 plus radical 2x plus a constant. I guess if you wanted to, you can add this constant, and we'll say we have a different constant, c sub 2, with radical 2x minus natural log 1 plus radical 2x plus a different constant. So c sub 2 is 1 plus the first constant, right? Mercy, that was a real challenge. Let's see how this next one goes. Hopefully it's not as bad. That one was hard. Okay, and then part B. Oh, it's an indefinite integral. If the denominator is our u, then du is 3. We don't have 3, so we'll balance it by dividing through. We can pull out the 5 and the 3. So let's do that. We'll put 5/3 here. And we've got a u on the bottom and a du on the top. But we need to change our bounds. So when x is 0, 0 there, u is 1. And when x is 4, u is 13. So we're going from 1 to 13. That's natural log. Oh, this one should have been first. It was a lot easier than the other one. Natural log of u from 1 to 13. These values are positive. So we really don't need the absolute value bars. Natural log of 13 minus natural log of 1. But natural log of 1 is 0. So end of the chapter. 5/3 natural log of 13. And we'll just stop there. Not sure what the decimal approximation is. If you wanted that, guess we could figure that out. So 5/3 times the natural log of 13, and that's about 4.2749. So just keeping up our skills with the calculator. There you go. End of chapter 7.